All right, so here we're going to work through a hydrostatic force problem. I've chosen problem 270 from your textbook. And in this problem, what's happening is there is a container which is in the shape of a pyramid, and the container is being filled with a liquid which is got a density less than water. It's got a density of 789 kilograms per cubic meters. So it's been filled up, and now this tank in the shape of a pyramid is completely filled, and you're being asked to figure out what's the force pushing on each side of this container, and where is the center of pressure. So it asks you for the resultant force and the center of pressure. So it also suggests that we use the formula method, which is it's a good suggestion for this problem. In that case, we can basically remember that the hydrostatic force goes as gamma h bar A. So we need to be able to interpret what h bar and A are. So why don't we draw one of these sides. It's going to look like this. It's going to have a bottom width of B, and it's going to have a height of 6 meters, but its length on an angle, if we look at it from the side, we're going to have something like this, where this is 2 meters. This is equal to 6 meters, and so this would be equal to the square root of 36 plus 4, or 40. So this length here is going to be a length of square root of 40. So why don't we call that length L for the force, since we haven't used L for any other variable. So we've got the width, bottom width B, we've got the height of this pyramid H, and we've got the length along the side of a pyramid given by L. Okay, so H bar is going to be the distance from the liquid surface down to the centroid of this area. So the centroid of this area, we call that C, okay? And it's going to be over here, it's going to be right about there. And we would expect that it's going to be located 2/3 of the way from the top, which is a height of 2/3 h. Okay, just based on the sort of what we know about the geometry of a triangle is that the centroid is going to be 2/3 from the fat end of the triangle. So in that case, h bar would be equal to 2/3 of h, which is going to be equal to 4 meters. Okay. And then the area is the total area of this surface. So the area is going to be equal to 1/2 the base times the height of a triangle. I'll write that as base times height of a triangle. But in this case, we have to keep track of the geometry along the face. So the area is sort of along this hypotenuse. And so in that case, the height of this, according to this formula, is going to be 1/2 times B times L. So that would be equal to 1/2 of 4 times the square root of 40. Okay? Or 2 times the square root of 40. So we can quickly see that then the resultant force is going to be gamma, which is this density times G times h bar times A. So that's going to work out to 789 times 9.81 times 4 times 2 times the square root of 40, and That works out to be 390 kilonewtons. Okay, so we can work through the resultant force using the formula method, as long as we interpret H bar and A correctly. Okay, so now what we need to do is interpret where the center of pressure is. We need to find that, and we can expect that that's going to be below the centroid of that surface. The center of pressure will be below that. And we can be helpful if we wrote that we have the center of pressure here. I'm sorry, the centroid of the surface is 2/3 of the way down, and then the center of pressure is going to be further below that, call that P. The variable y bar is measured along this surface. Let's use a different color for that. Okay, so that's this length L. But then this length here, that's going to be our y bar. And then the difference between that point and that point, that little gap there, that distance is yp minus y bar. And yp minus y bar is going to be expressed as the moment of inertia divided by y bar A. Okay, so now in order to figure out where the center of pressure is, how far down the surface, we need to compute y bar, and then we need to compute Ix over y bar A. So first of all, y bar, we knew that the centroid C is just 2/3 of the way down this triangle, but we're moving along the outside, so along the outside. So we're going 2/3 of the square root of 40. So y bar is 2/3 of the square root of 40 along the length there. And then Ix over y bar A. Ix, we'll have to go to our tables for that. So we go to our textbook, handy textbook here, go to the back and we say, well, okay, what's the moment of inertia for a triangle? It's 1/32 BA to the third. So we write down that the moment of inertia for a triangle is 1/36 the bottom width times the height to the third power. In this case, our height is, we call it L, and our bottom width, we actually use the letter B. So we're going to sort of we could write this as 1/36 times B times L to the third. So we can write this as 1/36 times the bottom width times L to the third divided by y bar, which was 2/3 of L, and also divided by the area, which is 1/2 B times L. Isn't that interesting? So now, if we do some cancellations here, those cancel, the B's cancel, and I end up with 1/36. This becomes 2/1. This becomes 3/2. So the ratio works out to be 36 divided by 3 is 1/12 times, that's all times L, 1/12 of L. So that means that the different distance from yp to y bar is just equal to 1/12 L. Y bar was 2/3 L. So that means the distance yp is going to be equal to 2/3 of L plus 1/12 of L, or 2/3 of the square root of 40 plus 1/12 square root of 40. And that works out to be 4.74 meters. Okay, So our calculation tells us that the center pressure is going to be 4.74 meters down this face, and so the resultant force is going to be looking like this. So this force of, where did it go? Somewhere we wrote down the total force. 390 kilonewtons. 390 kilonewtons is pushing up at that angle, and it's pushing a distance of 4.74 meters from the top of the tank. So now we have a point force acting on the side, and if you want to do structural analysis of the tank, you could have something to work with. Okay?